So yeah, I'm just going to give you a quick introduction to this. So I appreciate not everybody's been to one of these meetings before. So some people are new to Pipebots, and there's others who are from the water industry or not from the water industry. So just a quick recap of what we're actually trying to do here. So obviously, water networks are aging, both clean water and sewage networks, and they're deteriorating as we go forward in time. But there's lots of reasons why they might be deteriorating. Obviously, how they were laid in the first place, what materials they are, what service life they've been in, what loadings they've had, whether it's hydrogen sulfide in sewer pipes and so on. But these pipes are buried, so obviously it's difficult to assess exactly what condition they're in at any point in time. We've got some data from CCTV, mainly on the sewer networks, which is collected to give us some idea of that condition, but obviously that tends to be biased to pipes that you're expecting might be in poor condition, or the critical ones that you really want to make sure don't fail. On the water supply side, there's much less knowledge about the networks down there, and while we've got some sort of modern technologies like sewer bat, they still require us to sort of close off a lane in your road so you can pull up a manhole, have people on site to actually take those measurements. So you've got cost implications there as well. So, I mean, obviously in the last sort of 10 years particularly, there's really been a sort of move towards smart networks, developments in sensors, battery technologies, communications and data analytics are really being enabling this. And it gives you a lot more knowledge of how your systems are working. But at the same time, that's usually a knowledge of how they're performing rather than what the condition of those networks is. So there's a limited sort of amount of future planning you can really get from that. You can infer stuff from it, but there's probably a step change that we can make as we move forward into the future. So the real concept behind Pipebots is that we've not only got sensors, but they also move around those networks, and they're looking at condition of the pipes as well. So we think that if you've got regular monitoring of those networks, it's more broad, so you're covering most, if not all, of the network, you can get a much better understanding of what your network condition is and how those deterioration actually changes as you move forward in time, or what really influences that deterioration. So the future vision is for those swarms to be permanently and pervasively across those networks, looking at the condition and performance and updating that data regularly. So this would hopefully at least reduce disruption, whether that be through surveying or also through failures that are happening, reduce costs overall, and certainly increase the knowledge of the system, so we can sort of optimize the management of those assets and minimize failures across the networks. So Pipebots is arranged into 8 sort of themes. Theme 1 is the management theme, and then we've got 5 themes which are really sort of developing actual technologies. So we've got theme 2 is looking at sensors, mainly ultrasonic and acoustic sensing. Theme 3 is looking at robotics, so the actual platform that your sensors and so on sits on, how it moves around the network, and that effectively integrating that all the electronics and hardware together. Theme 4 is looking at the autonomous control, so how the robot moves through the network, how it decides where it's going to go, when you've got a swarm, how they interact. Theme 5 is looking at your navigation, so where are you in the network, where have you found a defect, sort of feeding that back into all the different themes, and that's looking at SLAM, simultaneous localization and mapping. It's easy for me to say. Then we've got communications power, particularly communication, so that's between your swarms and your robots, and obviously getting that information back out of your pipe networks. And the last 2 themes are really sort of more, I guess, desk-based, you could say. Theme 7 looking at the emerging science, so how it fits into the wider landscape, what governance issues there might be, and how it fits into business cases. And then theme 8, which is really where I'm focused, is linking to water industry, understanding the needs, and then also our real core sort of science in this is looking at, when we've got all this data coming out of the robots, what do we actually do with that? How do we change that data into knowledge, so we can better manage the assets as we move forward in time? So that's basically a very quick overview of what we're trying to do and how we're trying to do it. So as Kirill said, we've got some technology demonstrations now. Firstly, theme 3 is going to give us some progress on their robotic platforms and also deployment mechanisms which have been developed. So that's going to be from Andy Barber. Luan is going to give us some idea of the simulations that they've been doing with autonomous control. And then finally, Matt is going to give some progress of what they've been doing with the SLAM, with cctv data and simulations. And then finally, we can sort of come together and take some questions on that and have a bit of discussion through that. So yeah, I hope you find that interesting. Andy, if you want to take over.
Yep, hang on a second. Right. We got the right screen there. Can everyone see a big thing saying theme 3?
Yep, I've got that, Andy, thanks.
Lovely. So hi everyone. As Will pointed out, I'm Andy, and I'm sort of going to be running this sort of theme 3 section of this presentation. Theme 3 is, as I said, sort of covering more the robotic platforms as such, and what we've been doing on that side of things. I'll start with a brief history of what we were doing up until the last industry seminar, and then I'll focus more on our more recent developments. So first, we'll have a look at one of our first events that we focused on, which was the first sort of the project launch event, which is at the Royal Academy of Engineering in London back in 2019. For this event, we produced a number of different platforms, mostly small in size and scale, each with their own unique design feature, whatever that might be. It may have been sort of their locomotion style, their manufacturing method, or another facet. This was sort of our first experience of seeing what might be successful, what might be able to bear fruit for us going forward. Some of these demonstrators were more successful than others, but we were generally quite happy with the output. One of the things that was good about the event was talking to our partners in industry. We were able to really get some good feedback on what would and wouldn't be successful in the pipe networks and be able to use that going forward. Next, we move to 2020. That year started with our sort of first joint technical sprint project. In this, we wanted to be able to make an integrated robot that was able to take input from a number of themes across Pipebots. This was to be done over a 3 to 4 week gap in March of last year, with all the teams coming together at the end to integrate their work and be able to test it at iCare in Sheffield. Unfortunately, the COVID pandemic halted our work on this, and everything sort of came to a standstill for a while. Eventually getting back going when the country slowly started to open up again, when we eventually managed to do some tests with a few of the themes there at iCare in around about October time, just before we had our last industry seminar last November or October, around that time. The robot was shaped like a ball to be able to allow it to turn around within the pipe, and it also had wheels that surrounded the whole diameter of the robot to be able to sort of help combat the risk of the robot beaching in the pipe. It was able to travel in pipes that were 240 mils diameter and larger, and it was fitted with an array of sensors, cameras and speakers, as said, to be able to allow the other themes to be able to make most of this for their research work. The robot also had the capability of being either tethered or battery powered, and so yeah, everything came together and gave us some sort of nice feedback on where we were. That being said, we were generally happy with our results, but there were a number of areas that we felt we could improve. One of the things we'd like to do is be able to generate robots that can work within 100mm diameter pipes. That's about half the diameter of the robot, of the sprint bot that we had made. We also wanted to be able to produce a swarm of robots that would be able to work in a pipe network together, so they'd be able to complete a job more quickly and efficiently. Therefore, we wanted to be able to produce multiple small platforms with most of the capability of their larger counterpart. We also wanted these robots to be able to support autonomous control and to have a lot of them be able to move around in the same space. Now, if we had lots of robots in one area, having them all tethered would have potentially had the risk of them becoming entangled in each other. We would also have the problem with small robots needing the power to be able to pull their own tether, which would have been a challenge. Therefore, we decided we wanted to make the future robots battery powered, untethered. Having a robot that was untethered as well would then mean we would have a problem with power supply, because you can only have a limited battery size in a small robot. So we then decided we wanted to have the robots deployable from a larger system that could get them to sort of within the general area of where they needed to work. This led to our first production of our first swarm robot, which was around about June of this year. The robots there, you can see in the bottom left, were designed to be around about 50 millimeters in length, which is about a quarter of the length of SprintBot. It was also had the ability to be equipped with many of the systems the larger robot had, like cameras and lighting and some limited sensors. The method of locomotion we use for these is something called WEGs, which is a combination of wheels and legs. The idea being you can have the robot be able to mount sort of a reasonable step up in height, but with the simplicity of actuating a wheel. This robot was also able to be deployed from a sort of larger system. You can see in the top left, we decided to use a walking robot for this demonstration, which was for UK RAS's Live Lab Online, which is a nice sort of online event where the small team at Leeds were able to demonstrate a few robots from our lab to the general public. Whilst again, this was quite promising, we did find a couple of issues which needed to be rectified. We found that the center of gravity was too high on these robots, which made them unstable, especially going over rougher terrain. We also found there were a few inadequacies in the manufacturing and assembly process, which we wanted to rectify going forward. This led us to our current design. Now, the system we designed as a whole, we have named the possum system, sort of naming it after a marsupial. If you imagine you've got a larger animal carrying its young, we were going to have a larger robot carrying a number of small Joey robots. What you can see here is the Joey design. What we did was we updated the previous model we had to have a lower center of gravity to make it more stable. The way the robot was assembled was also overhauled. We separated the robot into 3 separate sections to help with assembly. We had the first section was the chassis and drivetrain, which was containing most of the mechanical components of the robot. We were then able to mount an electronics tray separately on top of that, which contains obviously the computing power and some of the sensors. And then we have a shell on top that kept everything together. In that locomotion package as well, we also had encoders to allow us to be able to accurately control the speed and positional control of the motors. And the electronics package also had custom and off-the-shelf components that allowed us to be able to use micro-ROS, which is a compact method of controlling a number of small platforms, or a number of robotic platforms at one time. The electronics also can use Wi-Fi, Bluetooth, either to be able to communicate, depending on which is most suitable in a certain situation. And this robot also had a series of range-finding sensors at the front that were able to cover a 90-degree area at the front of the robot to help with obstacle detection. We also have cameras to help with our SLAM work, some of which Theme 5 will be talking about later. And we also have on there an internal IMU, a microphone and temperature sensor for additional feedback. Although some of these, we could swap out some sensor systems for other systems if we felt they would be necessary in certain situations. Next, we have the mother robot of the possum system. Again, this what we've used here is a walking robot that is commercially available and we used for our earlier demonstration. However, this could be feasibly replaced with a different system if it was felt it would be more suited to a certain situation, like, say, for example, having a lift for dropping robots into a manhole. We also simplified our deployment mechanism. For this, we've just got a ramp that is able to sort of extend off the rear of the robot, which can then be lowered and can allow up to 20 Joey robots to be able to leave and enter the robot at any time. what we have now is we have a short video of some of our early testing for this. So what we have first is we have our mother robot being able to walk into position at an opening in the pipe. Now, you may not be able to get many of sort of openings like this in a natural real network, sewer network. However, as we said, we can always change the mother robot if required for a specific entry point to a pipe network. Once our robot's anyways in place, we can then have the ramp lower into position, at which point the joeys can then dismount from the ramp and go forth and investigate the pipe network for any blockages or problems. One of the issues we've found is the robots are quite hard to be able to, they find it's quite difficult to have them be able to be easily controlled in a pipe network, primarily because of the curved nature of the pipes. However, what we hope to have from Theme 4 is they are working on their system, system to be able to allow the robot to be able to move around areas like that with more ease. Luan from Theme 4 will be discussing that after me. Here we've also got a direct comparison between our little Joey robot and the sprint bots that we created earlier. As you can see, having a robot that's a lot smaller allows more robots to be able to go in an area. It also allows robots to be able to overtake each other if need be in one small area of pipe, and also poses much less of a risk of causing a blockage within a certain pipe area due to its small size. Anyway, what we have here is once our little robot has finished its work, it is then able to approach the mother robot again. It can approach the rear of the ramp and mount the sort of deployment system again. Once that's happened, the mother robot can then get into a position where it is able to walk off and send all our little robots to their next mission. And away they go. So that finishes my part of the presentation for Theme 3. Thank you very much for your time. I will now pass over to one of Theme 4.
Hello. Okay.
Yeah, I think we still got your screen, Andy.
Apologies, I'm trying to turn it off. Hang on a second. Stop share. There we go. Apologies for that.
Okay, so I share my screen. Can you see that?
Yes.
Yes.
Okay. So hello, welcome to Team 4 section of this demo. I am Nguyễn Thanh Luân, and I am a researcher working on Team 4 of Pipebots, which is to develop autonomous control for the project robots. In this presentation, I will going to introduce you to our progress and potential in making fully autonomous robots in pipes. So, let me see something wrong. I hide this. Okay, so as we has introduced, it is both expensive and time consuming to survey buried pipes with manual CCTV crawlers and visual assessment techniques nowadays. So this is because the CCTV crawlers needs human labor to operate, and it's only cover a small portion near the entry point. Also, the entry point cause surface disruption at the manhole opening. So in this project, our pipes robots are supposed to inspect and assess connection of buried pipes network autonomously. And Team 4 autonomous controller will help remove the data control. That is to remove all wire and cable, so robots can go deep into pipe network for inspection and mapping, and to remove remote control That means to remove human operators and road disruption, remove dependency to a wireless signal for remote control also. And we also provide long-term autonomous decision making under harsh and variable condition in the real pipe network. And we aim to control in both individual robot control level and swarm cooperative control level. So in this project, Team Force work closely with other teams. For example, in terms of technical integration, our controller interact directly with robot platform built by Team 3 and navigation system built by Team 5, and use communication and advanced sensing data from Team 6 and Team 5 to make decision and carry out tasks autonomously. And we in Team 4 we have developed an evolutionary robotic package which use an optimization algorithm to create new controller automatically. This package allows us to quickly create new basic controller for new robot platform. Then this allows us to observe emerging behavior that exploit the pipe topography and to take iteration from those behavior to integrate to our manually designed control algorithm. Then we have been training the Sprint 2 robot, the robot that Andy had just saw in 2020, with the controller of a neural network package above for navigating in pipes with blockage. The robot controller was trained to try different strategy based on natural selection, creating mutation with best fitness score when avoiding blockages. The controller is expected to evolve its behavior in pipe network. And then with the previous Sprint robot, we created an auto mode controller for it to navigate in pipe with T-junction, corner, branches, and dead end. The controller was implemented on the robot, and we carry out some experiment in the lab and at iCare pipes. And on the software side, Team 4 made ROS2 control package for the Sprint 3 software integration. And at the end, the whole team has the finished software architecture of generic Pipebot using industry standard software tools and methods. And we also created a simulation package including the Sprint 2 robot for equipped with different kind of sensor in auto-generated pipe network. This package is available for other teams to develop their software and then move on to experiment, including control, navigation, sensing, and mapping. And this was made with a collaboration with the team 2, 4, 3, and 5. Beside that, we also, beside our focus on high-level control, we also found the needs of the collaboration robot to accomplish complex tasks such as to rescue failed robot or to do elevation change or passing complex obstacle. So we design and is making a prototype for robot, a modular robot that can do modular cell assembly and do cooperative climbing on obstacle and elevation change. So today I will show you some simulation work because of the global softness of electronic components. Team 3 had just finished the circuit for the swarm robot, the WEG swarm robot. So while we are waiting, we built a platform, a simulation model of those swarm robots to develop control, and we will implement this control algorithm on the real robot when it's ready. And this simulation model has the same shape and size, sensor and function as the real robot. In today's simulation, we use mainly 3 range sensor, an inertial measurement unit, and motor position to as the feedback for autonomous control. The cameras and other sensors are to be used for other control strategies later on. This is the robot size compared in the 300 millimeter in the diameter of the pipe and on Andy hands as the real robot. So it has the same size and function. And so the robot is controlled autonomously in 2 levels. At the low level, the robot, the controller keep balance for the robot for it to adapt to uneven terrains, small obstacles, prevent a robot falling over, and keep the robot at the center of the pipe. It will not be it will not go in the wrong direction or fall over or flipping. The robot, the controller will keep the robot stable during high level control maneuver also. And at the high level control, the controller needs to make decision at current state and condition, and give the command to lower level to execute the maneuvers to at a certain circumstance. For example, in at this, let me remove the laser point. So at this clip, the robot is avoiding the obstacle on the right of the pipe, although its starting position was at the right side of the pipe, but it when it detects the obstacle, it avoids the obstacle to pass it on the left side of the pipe. And this is the other clip of that robot avoiding the obstacle on the left hand side of the pipe. And this is also similar condition, but the robot is on the very left side of the pipe, and it will autonomously avoid the obstacle and move on, passing the obstacle to go to the next step. And after passing the obstacle, it will steer the robot back to the center of the pipe, like this. So it will steer to the center of the pipe, and then when it detects the junction, it will the high level control will control the robot to make the next maneuver. And so this is the clip when the robot detects the bigger obstacle. When it covers almost all the section of the pipe, it will make the decision based on the obstacle size. So when it is small and it can set itself, if it can pass the obstacle, it will just climb over it. It will avoid the obstacle like previous clip. in this case, it will mark in the mapping process the obstacle and then turn back to find the other route or to explore the network or inspect other section of the pipe network. And so this is the robot when it is estimate its position at the T junction, and this is at the cross junction. It will decide what is the next action for the robot to move, and the lower level control will execute the maneuver for the robot to move on to the next step. And this is the robot when it detect the left or right branch when it move along the pipe network. And this is the video. So this is the robot when it's on the very left side of the pipe, and it detect the left branch and decided to go straight. But when it detect right corner, the right branch in the pipe network, it will turn to the right branch and avoid the left branch. So this is the behavior that we wanted the robot to move, so that it can autonomously explore the network, explore the whole network. And then this is the robot when it detect the turns or the dead end. This is at the dead end, and this is at the turn, the left or right turn. It will move the robot to at the dead end. It will mark the position and then turn back to find the other route. And but when it find a corner, it will move on and keep the robot at the center of the pipe until the end of the pipe. So and then this is the robot explore the network autonomously for inspection and mapping. So the robot will make all the decision at the junction, the dead end, the branch, the cross junction, to avoid the obstacle, turn over at the dead end, and at the same time it keep balance itself during the maneuver, and keep itself at the center of the pipe if there's no high level decision for the robot to move. And it will explore the whole network and come back to the starting point. And it's also the controller also can work on different kind of configuration. This is a smaller robot in a smaller pipe diameter, and this is a previous version of the web robot. And so that is the end of my part. I will pass over to Matt first, and then later on we will come back to the question. So let me stop sharing. Where is it? Okay. Okay. Thank you.
I think you're still sharing the screen. Oh, no? Oh, is this you talking? All right. Good morning, everyone. Let me see. So, am I sharing my screen?
Yep. Oh, good. Thanks, Matt.
Yeah. And you can hear me because you answered my question. So yeah, I'm Matt Evans, the postdoc in theme 5. So we're in charge of navigation. So when you think of the word navigation, you tend to think of what Luan talked about, which is sort of getting from a place to another. But within Pipebots, what we mean by navigation is localization and mapping. So I've got these slides out of order. But yeah, so for, you have localization, which is sort of where the robot is and where it's been and things. And then the mapping part is, what's the surroundings and where is it with respect to the world. And then theme 5 for Pipebots is doing that. So we're building maps and working out where the robot is within those maps of new pipes or pipes that haven't been explored before. We also want to incorporate prior map information because obviously there are lots of these asset maps available. Some of them might not be accurate, or it's not clear how accurate they are or how complete they are. So the idea is to be able to generate new maps, but incorporate the existing information where we have it. And then ultimately to do multi-robot mapping so that you can explore the environment much more quickly and efficiently by having robots spread out all over the place, and then combine that information so that we can build the maps more quickly and more completely over time. So then often in robotics, you have the problem of simultaneous localization and mapping. So that's where you start off with nothing and you have to build the map as you go, but also work out where you are within that map. So the difference is, if you imagine from the picture on the left, you're starting from A and you're going past C through to B. But then if you have a representation of that environment, like the one on the right, you can work out how the different locations relate to one another. That when you get to B, it's near C, and then you can work out how these things fit together into this one coherent map. So you call that loop closure, and that's basically the problem that you're trying to solve when you're building these maps and working out that the place that you've been to before is the place you are now. So typically that's solved in robotics with these very large vehicles with lots of sensors and lots of compute power, like shown in this car here. But we have certain constraints in the pipe environment. So one is what you call perceptual aliasing, in that a lot of the pipes look very similar, like these screenshots on the right hand side. And the pipes are obviously small, so you can't put lots of laser sensors and big computers down there. And obviously the prior information can often be wrong, and GPS doesn't work. So we've been working on using different types of algorithms. So in particular, focusing on visual odometry, which has been used in really challenging environments like for Mars rovers. So that's basically, you take a photograph and then you move the camera, or the camera's attached to the robot, you take another photograph and you extract features from each, and you work out how those features have moved from one photo to another. And then from that, you can work out how the camera has moved, and therefore how the robot has moved. So we've been developing methods based on these approaches for solving the localization and the SLAM problem in pipes. So in simulation, similar to what Luan was talking about, so we've built simulated pipe environments so that we can develop these mapping approaches. So we have similarly again pipes and manholes, and then you're a virtual robot inside the simulation here. And then the robot will start moving, and then you'll be able to see. So on the right hand side, you can see it's extracting visual features from the environment and working out where they must be with respect to the geometry of those points as they move, and then working out how the robot must be moving with respect to those points. So this is as moving through this virtual environment. You can see the sort of pipe shape and then the manhole shapes appearing in the simulated map. Let's let this run actually. So you can see here, we've added sort of visual textures to the inside of the pipe so that just to see how well the algorithms would do if you had, lots of stuff inside the pipes, and, how would the algorithms deal with going around corners and stuff. So you can see now as we zoom out, done a pretty good job. Oops. Let me see if I can skip to the right bit of the video. It's done a pretty good job of reconstructing the trajectory of the robot there and building up that map. But this is obviously a simulation, so it's not of particular, there are things about it that are very useful for us in developing the algorithms, but obviously there's lots of things about the real live sewer pipes or drainage pipes, which are different. So we've also been looking at taking going out and getting CCTV data. So this is from a team from Severn Trentwater, and then using one of these crawler type robots or camera rigs, deploying it into the pipe and then taking those videos, calibrating the cameras appropriately, and then using that as input to these odometry and SLAM algorithms. So this video here shows same again basically, but now it's from a live sewer pipe. So you have on the right hand side features being extracted in the green points, and then on the left it's projecting those points into the world based on the geometry, so that you can then work out how the robot has moved and how the shape of the pipe. So that's localization, and that works. That seems to work quite well, despite the water moving and things in the bottom of the pipe. And then the final thing, it's a fairly short presentation. So once you've been down one of these pipes before, let's pause it, you then have your sort of point cloud map, and then you want to work out when you visit that pipe again, do the algorithms suffer from this perceptual aliasing problem I was talking about, where the pipes all sort of look the same, or can the algorithms work out that this bit of the pipe is I've been there before, and work out where you are within the larger pipe once you have this prior map information. So if you revisit the same pipe again and you find a crack or a leak or a blockage, can you then report back to the operator how far, where along the pipe it actually is to any kind of accuracy? So that's what's happening here. So on the left hand side you have the black dots are the point cloud map that's been made, and then the red dots are the projection of the green points on the right. So it's able to work out that the robot or the camera is at this location within the longer sort of 50-meter length of pipe here, and it's it's operating a sort of sub-meter accuracy. At least we're still in the process of quantifying all these results, because you obviously have the tether. The tethers, we don't know how accurate the tether is, and you have, as we say, haven't got GPS. So there's lots of new experiments happening so that we can quantify how accurate these methods actually are. And that's all I have to say.